From the Library of Congress in Washington, D.C.
Good morning. I'm Michelle Catteray-Bradley, a reference and research specialist in the Science, Technology, and Business Division at the Library of Congress. I'd like to welcome you to today's program, Saturn's Moon Titan, a Future Abode for Life, in which we'll learn about the work being done by the Cassini spacecraft studying Saturn's moon Titan. In many respects, Saturn's largest moon Titan is one of the most Earth-like worlds found to date. With its thick atmosphere and organic, rich chemistry, Titan resembles a frozen version of Earth several billion years ago, before life began pumping oxygen into our atmosphere. Titan is of great interest to scientists because it has a substantial active atmosphere and complex Earth-like processes that shape its surface. The moon is enveloped by an orange haze of photochemical smog that frustratingly obscured its surface prior to Cassini's arrival. Since 2004, the spacecraft's observations have taken the study of this unique world into a whole new dimension. This program is the second in a series of programs in 2014 and is presented through a collaboration, now in its 8th year, between the library's Science, Technology, and Business Division and the NASA Goddard Space Flight Center. This talk will discuss what we've learned about Titan through NASA's flagship Cassini mission and the similarities and differences between Titan's exotic atmosphere and that of our home planet. Our speaker today is Dr. Carrie Anderson, Associate Chief at NASA Goddard Planetary Systems Laboratory. Dr. Anderson has received her PhD in astronomy from New Mexico State University in 2006, her master's in astronomy from New Mexico State University in 2003, and her bachelor's in physics from Arizona State University in 2000. Please join me in welcoming Dr. Carrie Anderson.
Thank you so much for having me today, and I'm truly honored to come here today and share with you a very exciting story about this amazing world of Titan. So I'm sure there's a lot of you who are probably familiar with Titan. It's Saturn's largest moon. It's the second largest moon in our solar system next to Jupiter's Ganymede. But what's really unique about Titan is that it's the only moon that has this thick, substantial atmosphere. And even more intriguing is its atmosphere consists of a lot of organic matter. Okay, so we're very excited about Titan because of all the organics in the atmosphere and on the surface. So this image I have over here, there we go, of Saturn. This is a Cassini ISS image, the imaging subsystem instrument. And I don't know if you've seen Saturn this way, but you see this line right here? Well, that's the rings edge on, okay? And you see these bands on the planet. Well, the sun's down here, and it's shining through, and the rings are casting a shadow onto Saturn. And it's something you don't see a lot, and it's just very pretty. But over here, this is, well, pretty much my true love, Titan. Here it is. It's this amazing smog enshrouded moon that is so exciting to talk about. So of course that's what I'll focus on. All right, I wanted to start with our sun. Here's what it looks like. It's really old. It's about 4.5 billion years old. And the way it actually burns energy is it's basically a nuclear reactor. So it's hydrogen fusion, okay, at the very center, the core of the sun. Here's a cartoon I put together showing the schematic. So hydrogen atoms, they fuse and they form helium ash. And this is the way in which the sun produces energy. And so you see it. So this will continue for about another 5 billion years. It's going to be quite some time. And then eventually, the hydrogen will run out. And so that'll kind of end this first stable phase of the sun, which we are very familiar with. And eventually the sun will enter its second stable phase, where it'll start burning helium in its core, and it'll fuse to carbon ash. And I'll talk about that a little bit later. All right, so I put this together for you guys, just kind of represent the solar system today. It's not drawn to scale, of course, but here's our sun, of course, and you step out from Mercury all the way out to Neptune. And what I want to do here is define the habitable zone for our solar system. And here's the blue region. So the way it's defined, if you're within a habitable zone, liquid water must exist at the surface, okay? Now, if you're inside of it over here, it's too hot. Water's going to boil off. It's going to be vapor. But if you're over here, it's too cold. Water will freeze. You'll have ice. And so you're limited to this narrow region, and you can see Earth is barely inside it, and Mars just misses it by a bit. But like all things, this too will change, and it'll change because the sun will evolve. All right, so after about 5 billion years from now, most of the hydrogen in the sun's core, it'll be exhausted, it'll run out, and the sun's gonna have to compensate for this. So what it's gonna do is it's gonna start to get bigger and brighter. And as this happens, Earth will get hotter and hotter. So when Earth gets warmer, the result is that the habitable zone as we know it will start to migrate outward. So it's gonna start migrating away from the sun out in the outer solar system. So, here's our question. Okay, this is going to happen. We can't avoid it. It's inevitable. But is there some other location in our solar system maybe we could harbor life on it? Well, how do we find that out? So as a NASA employee, what we do, we send robots. And that's the fun part. So we send robotic spacecraft to explore. Okay, so the very first, I would say, robotic spacecraft that were able to completely observe and encounter the outer solar system were the Voyager 1 and 2 spacecraft. I'm sure a lot of you remember that, the Voyager time, beautiful, amazing time. And so I want to show you a short movie from that time period at the Saturn system to give you a sense of this exploration. Okay, let's see if I can do this.
Mystifying man since the dawn of history, Saturn bears the name of the mythological god of the harvest, who reigned in the Golden Age. Traveling at more than 55,000 miles per hour, Voyager 1 arrived in November of 1980, only 12 miles off course after an interplanetary journey of more than 1 billion miles. Voyager's instruments found Saturn's atmosphere to be a cold ball of hydrogen and helium gases, racked by huge whirling storms and whipped by winds of up to 1,100 miles per hour. Saturn's magnificent rings, thought to have been the result of collisions between earlier moons and asteroids, consist of thousands of particles, swirling pieces of rock and ice, streaked like the grooves in a phonograph record. Voyager atmospheric scientist Dr. Andrew Ingersoll.
What Voyager discovered was the incredible structure in the rings. Saturn's rings are really composed of countless numbers of particles, ranging from the size of dust and perhaps larger particles the size of houses. These particles are constantly bumping into each other. These grooves are there because the rings are constantly being disturbed by satellites orbiting in with the smaller ring particles themselves.
As the Voyagers swept by, sunlight penetrated, backlighting and brilliantly illuminating the splendor of the rings, like the spokes of a gigantic Catherine wheel. Voyager 1 flew within 2,500 miles of the surface of Saturn's largest moon, Titan. One of only 3 moons in the solar system known to have an atmosphere, Titan may help unlock secrets to the origins of life. Voyager project scientist Dr. Edward Stone.
Certainly one of the more exciting discoveries at Saturn was the atmosphere of Titan. It's an atmosphere which is mainly nitrogen, like that here on Earth, but which contains methane, so that the photochemistry going on there today may resemble very strongly that which occurred here on Earth billions of years ago before life evolved.
By swinging around Saturn, after a close-up view of Titan, Voyager 1 was propelled out of the plane of the solar system and is now traveling toward interstellar space.
I just love that movie. So what happened actually? So the twin spacecraft, Voyager 1 and 2, were launched. And this is back in the day when there was more money available to launch these kind of flagship missions. But what was so neat about it was that Voyager 1, its destination was the Jupiter and Saturn system. And so it had just the right launch window, so it would fly by Jupiter as close as it could, and Saturn, of course, as well. And then after it encountered Titan, as you saw, it went out of the plane of the solar system. Voyager 2, you guys probably all remember, it was the Grand Tour, right? So it didn't fly as close to Saturn, but it flew by Jupiter, Saturn, Uranus, and Neptune. And there's, of course, tons of movies on those, which I don't have time to show today, but a tremendous, accomplishment. It was truly remarkable. And then when Voyager 2 got to Neptune, it flew very close to the North Pole, but then it kind of was shot like downward out of the plane that way. So you had Voyager 1 this, and you had Voyager 2 this way, and both of them, I believe, are almost entering the interstellar medium. So they're almost outside of what we define our solar system today. So that's pretty cool. All right, so let's see if I can move. Okay. So this is a Voyager image of Titan, and then I'll move on to Cassini, of course. But when I close my eyes, this is actually what I see when I envision Titan. And so when Voyager arrived, it had a camera on board that could see the same wavelengths of light that we see, our human eyes see. So if you're in space looking at Titan, this is pretty much what it would look like. This smoggy, orange, hazy looking moon. Well, that's because it's this smog-covered moon, and it's smog way worse than LA smog. I mean, there's a lot of smog on Titan. I mean, a lot. But it's full of organics, and that's what's so exciting about this moon. And so Voyager realized it couldn't get through the smog and see down to the surface. What's the surface look like? What's the lower atmosphere look like? Are there clouds? What's going on? So how can we learn more about Titan when we can't see through the smog? Well, there's more to the electromagnetic spectrum than meets the eye. I'm going to quickly talk about photons once, and then I'm going to move on, I promise. So imagine this, a stream of massless particles, what we call photons, and they travel in this wave-like pattern at the speed of light, okay? Photons are kind of weird. They're both particles and waves at the same time, but we won't go there. But anyway, so that is what we call electromagnetic radiation, EM radiation. So each photon contains a certain amount of energy, and this defines the different types of radiation. So for us, with the naked eye, we are right here in this, you see these two lines here, the visible? That's us. That's all we can see. So when you go to the redder end, over here, to longer wavelengths and lower energies, you go into the near infrared, mid infrared, far infrared, and then you go into the microwave and the radio. The opposite regime is over here on the violet end, and you can tell how it's much higher frequency here, and so higher energy, and so you go into your ultraviolet, your X-ray, and your gamma ray. Okay. So here's Cassini, when we have robotic spacecraft like this, we can take advantage of the EM spectrum. And so Cassini here it's pretty amazing. It's the size of a small school bus, so it's pretty big. And one thing that's really neat about sending spacecraft, when you go to outer space, you're in a vacuum. So you don't have to worry about anything aerodynamic. Engineers can sort of do whatever they need to do to get all the instruments on board to launch it, Not that simple, but anyway, it's kind of neat. And so Cassini, though, has this complex suite of science instruments, both remote sensing and in situ instruments. So remote sensing is like if Cassini's orbiting Saturn, let's say, and it's looking at the clouds or it's looking at something, it's receiving radiation, it records it on a detector. But an in situ measurement is when Cassini actually would dip into Titan's atmosphere, very high altitudes above the surface, about 900 kilometers or so above the surface, and it actually samples the atmosphere. So we have these fields and particles instruments that take the atmosphere and they analyze it. And they're able to come up with what the composition is at that altitude. So that's an in situ measurement. That's very exciting. And lastly, you can see this sort of circular thing right here. Well, that's the Huygens probe. Huygens was launched into Titan's atmosphere in January 05, and it had 6 different instruments on board to do science. And it descended the atmosphere and landed on the surface, and I'm going to show you a movie in a little bit about that. So the bottom line is, when we have these spacecraft, we can take advantage of a much larger range here of the EM spectrum. And so for Cassini specifically, we see from the UV here all the way out to the radio. Okay, here's a Cassini image of Titan. Very pretty. Same kind of thing that Voyager saw at visible wavelengths with what the naked eye could see. It's smog and shrouded, right? You can't get through it. But it's very interesting. It's very interesting what happens with Titan's smog or its aerosol. As you go to longer, redder wavelengths, the optical properties of the material actually start becoming more transparent. And we take advantage of that to penetrate through the atmosphere onto the surface. So if you go slightly into the near infrared, which is just outside of the red end of where we see, look what happens. You can see these are surface albedo variations on Titan. So as you're looking straight down, it's the clearer, but up here you're still picking up on some of the aerosol. But now if we go to even longer wavelengths, even more red, watch what happens. This is with VIMS, one of the other instruments. All of a sudden, it's a whole new world, okay? So that's just using different instruments with different wavelengths to tell a much broader, detailed story than what you ever would have thought if you only were in the visible. So, okay. All right, so I'm going to show now just a couple slides, kind of just representative of what we've learned about Titan since Cassini's been in the Saturn system. I mean, compared to Voyager, which was just, now remember, it was just one flyby, and that was all we got. And Cassini, which is orbiting Saturn, and it'll go and kind of fly by Titan, it'll fly by all the moons, the ring system, all kinds of cool stuff. So we have a wealth of knowledge we're gaining from this mission. It's an amazing flagship mission. And so this is one of the instruments. The camera is the Imaging Science Subsystem. And one thing about Titan, it is cold, okay? Titan so it orbits Saturn, which is 10 times the distance from the sun that Earth is. So what that means is you get a lot less flux from the sun falling on Titan than you do on the Earth. So the surface of Titan, it's about minus 290 degrees Fahrenheit. It's cold, right? But interesting enough, the pressure is very common to Earth. So if you were sitting on the surface, the pressure would be a little higher. You wouldn't, it's about 1.5 times what Earth's is. So you kind of would notice that a little bit, but you'd be able to survive on the surface. You wouldn't need a compression suit or something. Now the temperature's a different story because it's cold. Right now it's cold. We'll see what happens though. So, okay, so because it's so cold, water ice, there's a lot of water ice in the outer solar system, especially when all the planets were forming. And Titan, its mantle is mostly composed of water ice. I'll get to that in a little bit. But the bottom line is that the water ice takes the place of bedrock on Titan, okay? It's very hard and it's solid. And methane, because of its location in the solar system, takes the place of water on Earth. So right here, you see these bright white clouds, these streaks here? Those are methane clouds in Titan's troposphere. So the troposphere is the lowest atmosphere level in an atmosphere. So when you're on Earth, of course we're all on Earth, and you look up, I think so Titan so much. I forget about Earth. I'm like, Titan, It's all I dream it. It's probably unhealthy, but okay. So you're on Earth and you look up and you see those beautiful white cumulus fluffy clouds, right? Those are water ice clouds. On Titan, it's not water ice, it's methane ice. Similar process, but it's methane, not water. But there's methane rain. We have rain on Earth, and on the surface, there's liquid water on Earth's surface, and there's liquid hydrocarbons on Titan's surface. Liquid methane, liquid ethane, liquid propane, things like that. So even today, being so cold, Titan's the only other world in our solar system that has liquid on the surface. It's not water, which is what our goal is for the habitable zone down the road, but it's still liquid. It's fascinating, absolutely fascinating. All right, so next I want to show you a VIMS image, the Visible and Infrared Mapping Spectrometer. This is the one that can go to even longer wavelengths, the redder part of the spectrum. And it might be kind of hard to see here, but you see these dark patches right here? Can you guys see those? Those are lakes and seas of liquid, mostly liquid methane, liquid hydrocarbons. It's amazing. And right now, the season tightens in. These things tend to accumulate at the near the North Pole. So the North Pole is like right over here. We have one or two, I think, at the South Pole. I haven't kept up to date on that, but most of them are the North Pole. And that may reverse in time. 1 year on Titan is 30 Earth years, okay? So one season's about 7 years. It's very slow. And that's why we want to have something at the Saturn system ideally could stay for 30 years so we could see a full year on Titan. And then we could kind of understand these processes a little more. Will this repeat at the South Pole? You know, we'll see. So, okay, so that's the coolest part, I think. And then it's kind of hard to see here, but the greenish looking patches, that's that water ice bedrock I was just talking about. But what I think is so neat are these orangey patches. Do you guys see those? Those are the Titan equivalent of salt flats. That's what the scientists, I don't do this work with VIMS, but that's what is the latest theory about it. So on Earth, you have salt, it dissolves in liquid water, water evaporates, and you get salt flats. Well, on Titan, we don't have salt, we have aerosol. The aerosol forms in the atmosphere, I'll show you that in a bit, and once it forms, we think it's refractory. So what that means is it can't undo what it just did, right? It's not like an ice where you condense it and then you can evaporate it. Once it's formed, it's done. So it'll take time and eventually it'll settle on the surface, which it does. And so now this aerosol, organic particulate matter, has settled on the surface. It's dissolved, they think, in liquid hydrocarbons. The liquid evaporates, and you get your Titan equivalent of salt flats. So that's the idea with that, which I think is in itself really very interesting. Okay, this one's neat. This is a radar image. So the radar instrument operates in the radio regime of the spectrum. And you see, this is an impact crater right here. It's the 8th known impact crater on Titan. That's not a lot. And that tells you there's a lot of erosion going on at the surface. So it's an active surface. Plus, there's this immense, dense atmosphere pushing down, okay, on the surface. So that's probably why we don't see a lot of impact craters. Just like on Earth. You don't see it on Earth. It's a surface that's continually renewing itself. So the wide areas are the ejecta, and that's probably composed of water ice, maybe some ammonia ice, potentially some minerals, calcium, things like that perhaps. And then the reason I really wanted to show this for you guys is to really emphasize, see these black streaks, sort of? Those are dunes. They're dunes. How cool is that? So on Earth, we have dunes from sand, right? You have enough sand on the ground, wind blows it, forms dunes. Similar on Titan, but we don't have sand on Titan. We got aerosol on Titan, and we got a lot of it because for billions of years, Titan's atmosphere has been making aerosol, and it's just settling down to the ground, and it's layering. So this tells you the fact that there are dunes, you know right away there is a lot of aerosol material down there. Otherwise, it wouldn't be blown to make dunes. And that's something to just keep that in your mind. Okay, so here's I'm going to switch now to the Huygens Probe Descent. It's about a 4-minute movie. And I was going to show you pictures, but the movie itself, it takes it to a new level. And so I want to share that with you guys. See, I can't see where to hit play. There we go.
January 14th, 2005 begins with the Earth passing directly in between the Sun and Saturn. An opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser parts of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, two dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surrounds the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on, as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal in direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed, with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
Wasn't that amazing? I've seen it so many times and I still watch it. Truly amazing. Whoops. Okay. Okay, so now I'm going to switch gears and we're going to talk about the far infrared. That's what I do. Okay, so it's kind of not as exciting as the shorter, or the imaging and cool stuff like that, because we don't have cool pictures, we have spectra. And I've learned people don't like to look at spectra. It's not as pretty, but it has a lot to say at the same time. Okay, so the far infrared, as part of the thermal infrared, what does that mean? Well, the best way to describe it is imagine it's wintertime and you're sitting there in front of your fire and you are, it's cold, and you reach out and you feel that heat. It's thermal radiation, okay? You can't see it. You see the fire, but you can't see the heat. Well, in Titan's atmosphere, we have an instrument on Cassini called the Composite Infrared Spectrometer, CIRS. That's the instrument team I'm involved with. I'm a science associate on that team. And that's exactly what we do. We work in the mid and the far infrared. It's all thermal radiation, and we pick up on heat, if you will, coming from Titan's atmosphere. Okay, so I wanted to kind of give you another example of that. So let's imagine you got a couple different tuning forks. Here we go, and they're vibrating. Now, each of the tuning fork, as it vibrates, it's emitting sound waves of a given frequency. Okay, we can kind of all visualize that, and you kind of see the little cartoon there. So if you know the pitch of that ahead of time, you can identify which tuning fork it's coming from. Same thing with molecules and particulates in Titan's atmosphere. So now, same thing happens, but now let's consider a vibrating molecule in the atmosphere. It emits EM waves, not sound waves, but EM waves of a given frequency. And if you know the frequency, which we do because we have lab work that tells us this type of molecule will vibrate at this frequency, then you can identify the molecule it's coming from. And it turns out that from the far and the mid-infrared regions, that makes up the thermal infrared of the EM spectrum, it turns out to be the perfect place to look for all these abundant molecules. And that's what we do. So this is the only spectrum I'm going to show you, I promise. So I think it's very pretty, but that's just my personal opinion. But okay, so here's a composite spectrum. The wave number here, think of that as frequency units. And the intensity is just how intense each part of the spectrum is as you look at it. So you can see from the spectrum all the different frequencies of emitted radiation from the various molecules we find in Titan's atmosphere with SEERS. And then every type of molecule, it actually vibrates at its own specific frequency, and that comes off as a sharp emission feature, okay? So I'm going to walk you guys through these because I want you to keep an eye out for something repeating. What do you see repeating as I read these off? C4H2, diacetylene. C2N2, cyanogen. C3H4, methylacetylene. HC3N, cyanoacetylene. We're back to diacetylene, methylacetylene, cyanoacetylene, HCN, hydrogen cyanide. And then we have acetylene, C2H2, propane, C3H8, ethane, C2H6, ethylene, C2H4, methane, CH4, and of course now we have ethane again. What's in common? What is in common with all those molecules? Carbon? What's that? That's right. And nitrogen as well. What are those? They're organic molecules. Okay? So the more we... Hydrocarbons. So you get carbon, hydrogen, nitrogen. Those are all considered organic molecules. So the atmosphere, the more we learn about it, Cassini has offered a unique opportunity to really learn about this amazing world. And it is just smothered in organic material. In the atmosphere from the gases, in the atmosphere from the aerosol, the smog, and also on the surface because things settle to the surface. All the aerosol settles, methane rains out. All these nitriles, which contain C and N, rain out. I mean, it's just swarming in organic. It is an organic soup, just waiting to happen. It really is. It's pretty cool. It's like, oh my goodness, there's so much organic material there. Okay, so where do these come from? Where do all the organic molecules come from? And where's the aerosol come from? And that's a really good question. And now with Cassini, we have a much better idea about that. It's actually kind of bizarre, so just kind of bear with me here. So about 98% of Titan's atmosphere is molecular nitrogen, N2. Earth's dominant species is N2 as well. And then you have about 2% methane, which we don't have that much on of Earth, of course. Now, very, very high up in the atmosphere, 1,200 kilometers or so, maybe even higher, you have these species up there, because they're everywhere. And then what happens is very energetic UV photons from the sun come down and they hit the atmosphere. Energetic particles from Saturn's magnetosphere impinge on the atmosphere. Titan doesn't have its own magnetic field. Saturn has it has its own. And Titan only partially, as it orbits Saturn, encounters the magnetosphere. Okay? So it kind of runs into these energetic particles, if you will. So you have the energetic particles and the high energy UV photons impinging on the atmosphere. And what they do is they break up the molecules. They photolyze methane. That means they split carbon and hydrogen, split it up. They dissociate N2 into atomic nitrogen. Now, these particles don't want to be by themselves. They want to get together and recombine and make a molecule. So now the photochemistry begins. Boom. All of a sudden, we start to get simple organics. we get acetylene, and so forth. We get ethylene, here's ethane, HCN, hydrogen cyanide, HC3N, you name it, we start getting all these things. Hydrogens and nitriles are really starting to be produced. This continues, and all of a sudden, you're building up a benzene ring, okay? And other complex organics. So you're starting to multiply, you're starting to get bigger and bigger and make bigger particles. Now I want to call out here, benzene is extremely important, and we're going to come back to that next. This process continues, and you build up larger and larger ring structures, making more massive and more massive particles, until eventually things polymerize, and you form your aerosol. You form the smog, and that's how it's done. So basically from N2 and methane, very high up, and they get some energy, boom, they start chemistry. And that makes the spectrum I showed you from Sears, all those molecules come from this process, and that was in the stratosphere, so that was much deeper in the atmosphere than I'm talking about right here. But you get, so everything, even the aerosol, everything comes from this initial process here, okay. All right, so why is benzene so important? Well, it's that ring. Benzene is the simplest form of what's called a polycyclic aromatic hydrocarbon, PAH. What we know about PAH, so here's a benzene ring. Here's your carbon and then your hydrogens. So it's the ring part that's really important, because once you have that, and we've identified benzene in the atmosphere, we definitely 100% have benzene. Once you form it, it's kind of easy to start building bigger molecules. So all you got to do is knock off 2 hydrogens from each of the benzene rings. They're going to fuse together, and you're going to get, this is an example of naphthalene. This is going to continue, and it becomes a very efficient process to start making things like this. Okay, very large, it's a lattice. It's like a 2D, imagine it's like a 2D thing. This big lattice, and it gets larger and larger and larger. And also one thing, more connected with some of the work I'm doing back at Goddard, is that if you take off a carbon and a hydrogen, and you replace it with a nitrogen, we can really start making aerosol fast and making it abundant. So that would be called a PANH. So you have the PAHs and the PANHs. Anyway, this is how we think you build the aerosol eventually. It's a very efficient process. Okay, so I wanted to give you an idea, show a couple movies of a hydrocarbon, PAH, and just to see and look at it vibrating to give you a feel of how it looks at a shorter frequency or lower energy or higher energy. So I want to call it time for chemical calisthenics, because that's what it looks like. All right, so this is coronene. We've never seen this in the atmosphere, but it's just illustrative. So look at the wavelength here, 6 microns. That's a pretty short wavelength. And so what you're seeing is, you see all this motion here? It's kind of like this. So you have your carbon and your hydrogens that are kind of going like this, right? So if you were to look at this at 6 microns in a spectrum, you wouldn't know it's coronene. You would know you had a group frequency of carbon and hydrogen somewhere going. So you know you got carbon and hydrogen, but you don't know from what, okay? So what you do, you go to longer wavelengths. Here's 33 microns, you're getting longer, and all of a sudden, this is like a jumping jack. So can you see the difference? So now the lattice is making this motion, it's moving. The body of the material is moving itself. And if you go to even longer wavelengths, let's see if I can do that. At 100 microns, this is smack dab where I work on the Sears far infrared data. Look at it, it's like a trampoline. So you can tell we're in a very low energy regime, but look at this thing. So if you didn't know it was coronene, and you measured coronene in the lab, you would know it's coronene, because it's the lattice screaming at you, this is what I am, right? Okay, so that's kind of what's going on with the aerosol, but it's not as simple, unfortunately. Too bad, but we're working on it. So this is just an illustration here of kind of how the aerosol builds up. You kind of saw this before when I showed you. This has the blue here, that's nitrogen replacing a carbon and a hydrogen. But up here, you see this orange spectrum that says Titan aerosol? Well, that's my work. That's what I do. I inferred that from analysis of Sears far infrared Titan data. And the thing to look at, this thing right here, that is an emission feature from the aerosol in the far infrared at very low energy. So right here, if we can mimic that in the lab, we're on our way to discovering what the end game is. When the aerosol forms, and by the time it gets down deep in the atmosphere where I can pick up on it with Sears on Cassini, this is whatever it is screaming at me, this is what I am, look at me. But it's such a complex thing. It's not a simple lattice like you saw with Corny. It's probably going to be things, well, I call it aerosol gunk for a reason, because it's probably just multiple rings, this large network of rings, and they're probably all scrunched together, vibrating weird. So like instead of a tuning fork, you might have a cracked bell type of, thing. Like, oh my God, what is that? Well, that's what this is. And it's telling me, so this is what we discovered with Sears. And we didn't see that with Voyager because it didn't cover that part of the spectrum. But we found it with Sears. And so whatever it is, we have some ideas of what it is, but we didn't know exactly what it is. So what we've done, a few of us at Goddard has got together, and this is a laboratory aerosol we've made. And what we did, this is the first time, the fact that it's not perfect, but the first time we actually ever got signal, ever. This is the first time ever. We're getting something in the far infrared from material. This happened to be quinoline, I believe we started with, which is a PANH. And then we made the aerosol from that. And we were really excited about this because we're getting signal at the low energy end here for the first time ever. So we're on the right track. And then, of course, the aerosol will, settle down in the atmosphere and then it'll land on the surface, which you guys have already know, there's a lot of it sitting on the surface. All right, so you remember I mentioned earlier that probably most of Titan's mantle is composed of water ice. And the reason we think that, this is an artist's conception here of what the interior structure might be. You basically have like water-infused silicate core, and then basically all of this is water. Most of it's water ice. And we know that because Titan has a very low density. It's, I want to say 1.8 grams per cubic centimeter. Earth is about 5.5. And what that means, and Saturn is 0.7. So we all know Saturn can float in a tub full of water, right? Totally, it would float. If you could make a bathtub that big, it'd float. It's very low density because it has mostly hydrogen and helium, right? But a very small core, probably. But Titan is a larger density than Saturn, but much less than Earth. So we know because of that, it's got to have lots and lots and lots of water ice underneath. And that's good for us. That's a good thing. We want water ice because if we can melt it and make liquid water, we are on our way because all those organics are sitting there waiting for water, So that's a really good thing. Now, so as the sun evolves, like I mentioned in the very beginning, and I'll get to that next, the ice will melt. I'm not sure if it'll all melt, but a lot of it will melt, and you will have liquid water. And so then you'll have liquid water sitting on the surface with all these organics in it as well. And from some lab work that's been done on Earth with laboratory aerosol analogs from the lab, because we don't know exactly what the material is, of course, but we can try to reproduce it, that if you just let this organic particulate matter just sit in some ammonia water or in some ammonia and some water, it'll make amino acids. And amino acids, amino acids, that is what people think are the precursors for life, and they contain carbon, nitrogen, oxygen, and hydrogen. Titan has all those. It's just waiting. It's ready to go. Okay, so how long does it take to form life? I don't have that answer. I don't think anyone has that answer. But we can read about it and see. So I did some reading, and there's some fossil evidence that this happened as early as 800 million years after the formation of the Earth. That's like 3.5 billion years ago. Okay, that's a long time. Now, other studies suggest it could be as early as 200 million years after the formation of the Earth. But what we know that is inevitable no matter what is that from about 12 to 13 billion years, once the sun became a star, when it started to burn hydrogen in its core, because of its evolution and what it's going to do, the habitable zone will inevitably reach Titan. And that is a yes for us. We really, really want that. That is going to happen, definitely, in a little bit. So, I imagine like when this happens, we'll like have the Enterprise starship, and we can just fly off to some other galaxy. Who knows? you know, and maybe just leave our solar system. But okay, so that is a definite. That is going to happen. So to kind of wrap up everything, I wanted to come back to the schematic. But what looks different here? The sun. Sorry. What looks different? Yell it out. There's no Earth. Where's Mercury? Where's Venus? Oh, it got incinerated. It's gone. Bye-bye. No, it's going to eventually, the Earth, there's a lot of debate. Will the Earth be incinerated when the sun starts to evolve and gets bigger and more luminous? Well, some people think no, and some people say yeah. But if it doesn't, all the oceans will evaporate. They'll boil off. All this air, liquid water that turns into vapor will go into the atmosphere, and you're going to have a runaway greenhouse effect, probably just like what happened to Venus. So either way, we got to pack our bags and get moving because it's not going to be good. So from what I can tell, so the sun's going to get much brighter and much bigger as it evolves. You probably heard about the red giant phase. It's going to ascend the red giant branch, okay? And as it's journeying on the way up this branch, the habitable zone is going to migrate outward away from the sun. And by the time the outer region of the habitable zone reaches Saturn, from that moment in time, from when the inner part of the habitable zone, the inner region, reaches Saturn, it's about 100 million years. So Titan's going to have about 100 million years to form life. But remember, at this moment in time, the water will melt, or the ice will melt in the mantle. A lot of it should melt, and you should have liquid water. And we have all those organics just sitting around on the surface just waiting for the sun to heat it up, right? So that's exciting. It's 100 million years. You think, oof, it's kind of short. However, on Earth, I mean, it is in this standards, right? But on Earth, it was hard for life because it had like lava and all these explosions, and it was hot, and it was uncomfortable. Well, on Titan, everything's waiting there. It's like, okay, just going to be patient. Just whenever the sun does its thing, come on, heat it up, you know. So it's different. So 100 million years, maybe, who knows? But okay, so that 100 million years will pass, and the habitable zone will keep marching its way outward, okay? And it'll end up, by the time the inner region gets to Uranus, this is when actually this picture is going to look like this, and the sun's going to be pretty much at the Earth's orbit, the radius of the sun. Now, what's happened, though, to Titan? Where is it? It's over here still. Uh-oh. It's to the left. That's not good. Because what that means is all that wonderful liquid water that we were waiting for like 13 billion years, it's going to probably boil off. It's going to evaporate, and it's going to enter into the atmosphere. So who knows what happens when there's water vapor in the atmosphere? What does it do? Is it a greenhouse gas? Yeah. Just like methane, just like CO2. So it's going to heat the surface. And imagine half the mass of the moon entering the atmosphere in water vapor form. It's a lot of mass. So it's going to get pretty hot. So once, okay, so just keep that in mind. And then we're going to, okay, so once we get to Uranus here, the sun's going to go, oh, I'm done. It's going to have this thing called a helium flash. It's going to go poof. And then helium is going to start fusing into carbon in the core. And the sun's going to go, oh, I'm more comfortable. It's going to reach equilibrium and go, I'm much better now. Okay, I'm cool now. It's good. Let's do this for a billion years. So that's what's going to happen. So when that happens, and it's like, whoo, you know, because it's going to get really hot there. When it starts burning helium, that's good for Titan a bit, because now the sun actually contracts. It's not as big. It's not as luminous. So what's going to happen? The habitable zone's going to go up. Let's reverse. And it's going to move back. And where's it going to end up? Right there. So it's fantastic for Titan, in a way, because it's going to stay like this. The sun will burn helium in its core into carbon and oxygen for 1 billion years. And so that's kind of a long time. That's pretty good. But here's the question. So I pose it. Here's the fundamental question. Because of the greenhouse effect that is inevitable, that will happen on Titan, does that inner boundary that you just saw, does it move back outside of Titan's orbit? Well, if yes, then Titan's going to fry. So that's too bad for Titan. But if no, well, maybe life has a real chance on Titan during those 1 billion years. And I don't have those answers for you. And I actually really hadn't even thought about this and talked about this talk together for you guys. But I'm going to go crunch some numbers, and I'm going to try to narrow in on this and see if I can come up with a more definitive answer. So stay tuned. Thank you.
Yes, I'm sure that we all have some questions for Dr. Anderson, so please, if you repeat yourself, I mean, Dr. Anderson,
Repeat the
Carrie
question.
will repeat the question afterwards, so just right down front.
As I understand, some scientists think that Europa, which is a moon of Jupiter, may harbor some kind of primitive life form in its ocean beneath the Earth's surface. Do you think that's a possibility?
So the question was that there are some scientists who it's been suggested that Jupiter's moon Europa, which we all kind of think it has a subsurface ocean below the frozen solid surface, could harbor some life or some bacteria in there. Well, I don't know, because that's how the first step is, how do we define life? If it's like microbes, I mean, Jupiter is 5 AU from the sun. It's 5 times the distance that we are from the sun. So there is that, we think there's that liquid water underneath the surface. And I don't know what happens within that itself. But in terms of life flourishing on it, if it's life like we know it, I wouldn't think so, only because it's small. Europa is really tiny. It couldn't contain an atmosphere. It couldn't hold an atmosphere. Like Titan's larger than Mercury. I mean, it's big, you know. And it's also it's much warmer at Jupiter. And Jupiter is really, it's got very strong magnetic fields. It's actually very hostile environment, I would say. You know, you think of its moon Io, which has all those volcanoes. I mean, Jupiter's very hostile, that environment. I mean, I don't know the actual answer to that, but if we're going to evolve to where we are, it's not in the habitable zone. Liquid water cannot exist on the surface, and Europa could never have its own atmosphere. It's too small. You need a larger body to have the gravity to retain that atmosphere.
But the question is, that it wouldn't, without the atmosphere, I mean, this is below the surface.
Mm-hmm.
Would you rule out the existence of microbial?
I mean, I wouldn't. I actually, the longer I'm in this business, no, I wouldn't. Because think about on Earth, when we dive very, very deep, like, what is it, 7 miles down or something, the deepest, you know, the depths we go to, and they find these organisms that barely get any light. And there's life down there, right? Scientists were completely bewildered, because how can they survive? But so I wouldn't rule anything out. In fact, when I think about it, we're just one planet, and we're a small planet, and our sun's a dwarf. It's a little guy, right? It's one star. There's billions of stars in our galaxy, and there's probably billions of galaxies in the universe. So I would say there's so much opportunity for life, and that's how you define life. But, I mean, you know how the saying is, the sky's the limit? Well, the sky's not the limit. You know, we got this universe. So I would say absolutely. I mean, I don't work on Europa and that part of that type of thing, but, I mean, we would, well, with the potential flagship that might go to Europa and study it, we will know a lot more about its environment.
While we're at it, you know, mentioning, what are the other 2 moons that have an atmosphere? I was thinking Europa was
Yeah.
one, but I guess it's not.
When I heard that, I went, huh. I'm a bit of an atmosphere snob, I'll be very honest. So people say Mercury has an atmosphere. It's tenuous. Kind of, right?
Totally did it.
Yeah, well, people would say it does. Trust me. But it's tenuous. It's like 10 atoms. I don't know. I don't know. But it's it's a low density. So that's actually funny, because that's how I got into planetary astronomy, was by studying Mercury. Anyway, long time ago. But, well, Enceladus potentially could, because it has those geysers of water ice that spews out into the atmosphere.
That Uranus is
No. That's no. This is Enceladus, is Saturn's moon. You're thinking of Triton, Neptune's moon. Triton has these geysers. So Neptune is 30 times the distance from the sun that we are. I mean, it's super cold out there. But Triton, it's one of its, I think its largest moon. It has these geysers, and Voyager found that actually when Voyager 2 flew by. So it has those geysers. So I think Europa, I don't think Europa has geysers, not that I know of. So my guess would be Enceladus and Triton.
I have a simple question. Why did NASA pick Cassini as the name for spacecraft?
Oh, probably from oh my God, I'm blanking on the first name, of course. Do you know? Yeah. Oh, why did NASA pick the name Cassini? And I should definitely know this answer. So I know for Huygens, was it Christian Huygens, right? And Cassini, do you know the answer? Go ahead.
I think so. It's an Italian astronomer, and Galileo named the Cassini moons, I think.
Well, the
Cassini stars or something, but anyway, Galileo referenced Cassini because of his association with Jupiter.
So Galileo, the Galilean moons on Jupiter, of course, Callisto, Europa, and not Enceladus, Ganymede, and Io. Those are the Galilean moons for Galileo. And so you're thinking that, I'll Google it. Where's my phone? It's a good question. I hope the project doesn't witness me not knowing that answer.
The gentleman. Yeah.
It probably does.
Over there.
The Huygens movie mentioned it, but there's a net loss of methane from Titan.
That's right.
Sort of debate on terms of whether it's being replenished or not.
Yes.
What's the current theory on that? And the concept that maybe unlike it would actually lose its entire atmosphere in another 15 or 20 million years. And then second question, in terms of cryovolcanism, which is also debated, how would you, as looking at the atmosphere, tie that into the subsurface ocean and then atmospheric dynamics with respect to aerosols and other processes?
Okay, so the first question then, tell me again, I'm sorry. Methane, right. Yes, methane is okay, so those reactions you saw when you use photolysed methane and you dissociate N2 and you form the aerosol and everything else, that's assuming we have a replenishment of methane coming up from below on the surface and into the atmosphere. So methane is a unique gas. It's the only one that has a surface source. We don't know what it is. Well, we think we know. We have some ideas. But everything else, so methane makes everything else, right? Those all form from methane high up. So you have some source putting methane up into the atmosphere. So all those lakes we found, there's been some, I think, calculations done to think that maybe those northern lakes and some of the southern ones that are full of liquid methane are partially responsible to cycle it through because methane just rains out. And then if you can recycle it back through up to the top of the atmosphere, you can continue your process. So there has to be a resupply if we want to continue the atmosphere, just like you said. So if this is a normal thing and this happens, it's going to continue happening, we've got to have a resupply from the surface, subsurface reservoir, and probably the lakes, and it could be something underneath. Think of like a geyser kind of thing, right? But the other view is maybe we're just catching Titan. It's a snapshot of it won't resupply the methane. It's just a snapshot in time. It just happens to have what it has now, and it'll eventually go away. So, I don't think we have any more information other than the lakes. Those were like a very new thing for this specific topic. And the cryovolcanism, tell me again, you want to know how that's connected with?
In terms of the subsurface ocean and how that might be related to replenishing the methane and then the hydrological cycle such as it is.
Well, there's never been a definite, there's been some thought about a cryovolcano that will spew water, ammonia, and methane into the atmosphere, right? But we haven't, as far as I know, we haven't conclusively found one. There's been thought about it to replenish the methane, but I think that was ruled out. There wasn't a cryovolcano. But for the water iso, if that artist schematic is true about what we think of the interior, you have a solid water subsurface first, then a potential water ocean that's decoupled from, I believe, and then you have another water ice layer. Then you have the water-infused silicate core. So once water vapor gets up there, it's going to photolyze pretty easy, and I don't know about the connection with methane exactly. Although, if you photolyze water, you're going to split up hydrogen and oxygen. So when you photolyze methane, you're going to have a bunch of free hydrogens running around that will want to recombine. But I don't know. I don't think there's a connection right now with resupplying methane from that, since we haven't really conclusively found that on the surface.
I kind of a simple question, which is it's a two-part, a clarification and a question, which is you said that Titan doesn't have its own magnetic field. My question is, does it share a magnetic field with Saturn? And the question is, Earth does have its own magnetic field. Is it clear whether human species can survive without a magnetic field?
Okay, those are really good questions. And so, the first question was, does Titan share? Titan itself does not have magnetic field, so does it share Saturn's? Well, no. Saturn has its own magnetic field, and it's pretty large, right? And so Titan, I believe it's about 20 Saturn radii from the planet. So it's close enough that when it orbits, it takes 16 days to orbit Saturn. And part of that, about half, I believe, is spent inside Saturn's magnetic field. So it's shielded from a lot of the sun, a lot of stripping away the atmospheres when it's inside a magnetic field, but when it's outside of that, it's no longer protected. And so that won't ever change. So when you have like solar wind coming through and can strip off top of atmospheres, if it's outside of that, it is affected by that. But Titan's atmosphere is extensive enough that this hasn't been a problem. I mean, you definitely are losing atmosphere at the very top, definitely. So it's partially, so it doesn't share, but it does it's embedded in Saturn's for part of its orbit. And then the second question, yes, so magnetic fields are really important. At least on Earth, it's very important. I mean, that shields us from a lot of the harmful UV photon things coming out of the sun. And that's a good thing to have, that you have that kind of shielding mechanism. So if you don't have that, then you're just exposed to whatever the sun throws at you and whatever could strip your atmosphere.
Yes, you showed a big ball of ice on Titan now. When that does melt, when the sun expands 100 times its current diameter, will it be a big ball of water? Do you expect there to be a landmass anywhere? And if so, is there a future, or what's the future outlook in terms of advanced life 5 billion years from now when the sun expands?
That's a really good question. So the question was, when the sun does enter into its red giant branch phase and it's ascending the red giant branch, and then the sun expands and of course luminosity increases, will all of that ice in Titan's mantle melt? And when it does, what will be, what do you really call, can you get life? Where is the surface? And these are questions I was just asking myself like 2 days ago, actually. So, I mean, it's a lot of speculation on my part. Until, like I said, it's like I can really go in and just kind of do some more calculations, have a better feel for it, and maybe consult a stellar physicist or someone as well. But the idea, I think, is because Titan has that very low density, I do believe a lot of the solid body of Titan is water ice. And when the sun will heat that up, it's inevitable. To what extent, I'm not sure. Like, will it do 50%, 20%, 80%? I'm not really sure, but I do know it will melt. And so if we're to take the extreme end, if it all melts, then the core, the top of the core would be the surface. If you'll have that and then maybe liquid, an ocean, and then that would be your surface. But if, so it depends on how much melts and what you want really to define as surface. But this is what's interesting, though. Think about a gas or ice giant. Think of, let's say, Saturn. It's got a rocky core of heavy stuff, tiny, and then it has all this extended atmosphere of light gases, right? And so Titan may not be so different, but just a smaller version of that if the entire mantle were to melt. And then once the habitable zone left Titan, if that all boiled up into the atmosphere, I really don't know how it would be so different other than composition from like Saturn or a gas giant. It could be very similar, and the pressures could be so large and so high when you're deep down by that core, which we call the surface. You couldn't survive down there with all that pressure. just to the sheer mass weighing down on you. So that's a good question. I really can't answer it because I'm trying to understand it myself. But it really depends on, I got to look at temperatures, the amount of luminosity that'll fall on Titan, that's a big thing. And then how long Titan's going to be in this condition, things like that. So, and I think that, like I said, I think the first round of the 100 million years, I think it's potentially doable when there is liquid water on the surface, and it's maybe all liquid, a big one ocean or something. And after that, when the billion-year time frame comes around, that's up in the air. That would be ideal time-wise to get life. It's so much longer. But will there even be any liquid water? And maybe, like I said, it'll all be in the atmosphere, and then we're kind of hosed maybe at that point. So we don't know.
It's always the scientist's answer. I'm sorry.
I'm not really sure.
One more question, and then we'll end.
We're talking from the assumption that Titan spins on its axis, or is it a fixed? Or is it a fixed moon? And how would that affect the development of life?
Well, so Titan does rotate 16 days, and it also takes 16 days to revolve around Saturn. So it's always the same size, tidally locked, okay? And so it does rotate, though. It's very slow. It's what we'll call a slow rotator. So that's one of the big differences between Titan and Earth right now, is that Earth is a fast rotator, so is Mars. One day, boop, done. Titan's like Venus, kind of the solid surface is slow. And so that changes. One thing that changes, at least present day, is how the energy is circulated through the atmosphere. And that has effects on how you get different seasons and how you move material and things like that. In terms of life, I don't know I don't think that would have a large effect on if 6 billion years from now, life does evolve. I'd be more concerned with how much flux falls on Titan from the sun and how large that is. But in terms of rotation, I think that'll be okay.
Again, thank you very much, Dr.
Thank you.
Carrie Anderson.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.